Okay, welcome back to our past year discussion. This is going to be for the course module SP015 for the Malaysian matriculation certificate, and this is the past year from 2019 and 2019-2020. All right, and this is going to be on questions with regards to oscillations and waves. So we're going to talk about simple harmonic motion, we're going to talk about progressive waves, we're going to talk about Doppler effect. All right, okay. So let's get into it. Let's look at question 8. So this is from question 8, 2019, 2020. 8A, we have a question on simple harmonic motion. Right, so we have the question says the figure shows a potential energy of a 0.5 kilogram object that undergoes a simple harmonic motion. Okay, so right off the bat, the question is talking about potential energy, and potential energy for SHM, or simple harmonic motion, is going to be U equals to half m omega square x square, and then of course the m is going to come from here. All right, the question goes, determine the velocity of the object when time t equals to 2 seconds. So I do apologize, the typo there. And the kinetic energy of the object when displacement is equals to x equals to 1.5. All right, so first things first, I just want to write down that U, or the potential energy when x is equals to 2, is equals to, so I'm just going to match it right up here, 2 here, 6 here. So the potential energy when x equals to 2 is 6 joules, right? That's going to be helpful later on. And of course, I want to write down for other values as well. For example, x equals to 3 meters, so it's going to be 13.5 joules. That's just for future references. Okay, so if I were to determine the velocity, I will need to work out the equation for displacement. That's priority number 1. So let me just part 1. Okay, I'm going to talk about velocity, but before I look for velocity, I need to know the equation for displacement. And the equation for displacement, the general equation, is going to be xt equals to a sine omega t. Okay, so A is fairly direct to find. You can find it from the diagram or the graph, right? A is going to be 3 meters. Okay, and then omega, on the other hand, I can calculate using U, M, and X. All right, so let me just split it up here. For omega, I can use U when x equals to 2, right, is equals to 6 joules. And that is going to equal to half, and then mass, so 0.5, then omega squared, and then of course I'll have x squared, and x squared here is going to be 2. All right. Okay, so if I were to solve for that, right, let me just rewrite it. So 6 equals to half times 0.5 times omega square times 2 square. If I were to just calculate that, what I'll find is that omega is equals to the square root of 6. Okay, so now I have a general equation. I have x t equals to 3 sine square root of 6 t, which is great. All right, I have that equation. If I were to look for velocity, all I need is to differentiate this equation. Differentiate this equation with respect to t. So I'm going to have v equals to dx over dt. All right, and that would leave me with 3 times square root of 6 cosine square root of 6 t. Okay, so now what I want to do is I want to look for the value of v when t is equals to 2 seconds. All right, so 2 seconds, that is equals to 3 times square root of 6 cosine square root of 6 times 2. Okay, and that would leave me with a value of, again, I'm just going to clarify, this is t equals to 2s, approximately 1.363 meters per second. All right, so that is my final answer for that particular part, which is time equals to 2 seconds. Okay, so now what I want to do is I want to look for when the displacement is equals to 1.5, the kinetic energy. Now, for the kinetic energy, which is going to be EK, I know my equation is going to be 1 over 2 m omega square a square minus x square. I know this because half m omega square a square is just the total energy. All right, so what I can do is I can simply substitute the values in. So I want to look for EK when x equals to 1.5. That is going to be half times 0.5 kilograms times square root of 6 squared, so that is squared, right? Omega square. Okay, and then I'll have a square, so 3 square minus x square, 1.5 square, and that would leave me with 10.125 joules. Okay, so we have calculated the value for the magnitude of velocity, so that one, okay, when t equals to 2, and we have calculated the kinetic energy when x equals to 1.5, right? So that settles 8a. All right, so let's move on to 8b. Okay, so here's the question for 8b. We have an oscillating pendulum, right, with a length of 0.3. So let me just label that right now. I'll have L equals to 0.3. And then I have the mass of the bob to be 0.24 kilograms. Okay. And then I have a total energy, so UT equals to 0.06 joules. Okay, so for a pendulum, your equation for period is going to be 2 pi with L over G square rooted. Okay, and then what else you need to know is that omega, right, is equals to 2 pi over t. Now, the reason why we need omega is the same reason we needed it for the question, for the previous question, which is that our ut is actually equals to half m omega square a square. And now we're looking for the amplitude. So that's why we have total energy. We know what is m. We do not know what is omega, and we can find omega from t. Okay, makes sense? Makes sense. So if I substitute this equation into here, what I will have is omega equals to 2 pi over 2 pi, and then multiply by the square root of g over L. Okay. Alrighty then, I can cancel them out. what I'm left with is omega square equals to G over L. All right, so I'm going to rewrite the total energy, which is equals to half m omega square a square. I know my omega t is going to be 0.06, so 0.06 equals to half times the mass of the bob, which is 0.24 times omega square, and omega square is going to be g, so 9.81 over L, so L is 0.3, and then I'm looking for a square. So if I just rearrange that and calculate it numerically, what I will find is a square is equals to 0.0153 meters square. Again, I can take the square root of both sides, and I'll have a equals to 0.127 meters. And that is going to be my final answer. Okay, so what did we learn today? We learned that when dealing with oscillations, it's generally useful to talk about the angular frequency. Okay, because in both questions 8a and 8b, right, it was useful for us to focus our work on omega. All right. Okay, so let's move on to question 9. Right, and this is a question on progressive waves. Now, the difference, again, I just want to emphasize that the difference between simple harmonic motion and progressive wave is that even though simple harmonic motion uses trigonometric functions to express themselves, for progressive waves, we have two variables. Rather than having simply displacement, we have in time as well. Okay, so that means when we talk about progressive waves and we talk about the equation, we will generally have y, x, and t. All right, so let us just look at the equation, look at the question. All right, the figure shows a graph of displacement y against distance x for a progressive wave propagating to the right in a string with mass 920 grams, length of 3 meters, and tension of 50 Newton. Determine the progressive wave equation. So when you're asked about the wave equation, it's generally useful to simply write down the general equation first. Okay, so the general equation for any progressive waves is going to be y xt is equals to a sine omega t minus kx, right? The reason why I put minus here is because the wave is propagating to the right. So let me just emphasize that a little bit more. So I'm putting it negative because the wave is propagating to the right. Okay, so moving on. I need to figure out, because A is fairly direct, I have A to be this value. So this is going to be 0.12 meters. T and X, I don't need to worry about them, but I do need to worry about omega and X. Okay, so because this is two wavelengths, this is 50 centimeters, right? From the diagram or from the graph, I can work out that 2 lambda is equals to 50 centimeters. That would also mean that our wavelength is 0.25 meters. Okay, right off the bat, right off the bat. And that means we can calculate our value for the wave number, right? So the wave number is simply 2 pi over our lambda. And that is going to be 2 pi over 0.25, and that is simply 8 pi. Okay, so that's fairly direct. The second part, right, where we have to look for omega is a little bit longer. Okay, So let us attempt it right now. So we have omega, right, equals to 2 pi f. This is how we relate between angular frequency and just frequency. All right. So where can we get this frequency from? Now, for any wave, for any progressive wave, generally what we will have is v equals to f lambda. Okay. So let me just write it down here. I will have v equals to f lambda. Now, the velocity of a wave, specifically for a string, is going to be equal to the square root of tension over mu. What is mu? Mu is the mass density. Okay, so mu is going to be the mass density. Now, if I simply rearrange this equation, what I'll find is that, let me just continue it here, omega is equals to 2 pi, right, multiply with 1 over lambda, and then that multiplied with the square root of t over mu. All right. Again, what is mu? Mu is actually the mass density. I'll write it down here. So mu is equals to mass of the string over the length of the string. All right. So that means our omega is simply going to be 2 pi over lambda multiplied with t over m over L. Okay. All right. So now what I want to do is I want to substitute those values in. So 2 pi over lambda. Lambda is 0.25. And then I have the square root of tension, which is 15 over m over L. So m is simply going to be 0.92. And then I have the length of the string, which is 3 meters, right? I want to square root the whole thing. And what I will find is going to be omega is equals to, let me check, so 120 multiplied by 5 over 23 pi. In general, I like to keep pi as its own and fractions as they are up until the end. And the reason for that is because it preserves the number, sorry, the decimal points. Okay. So now what I want to do is I want to, okay, include omega, the values of omega and k in our progressive wave equation. So our progressive wave equation is going to be y xt equals to 0.12 sine, okay, and then I'll have omega t, so that is simply 125 over 23 square rooted multiplied by pi, and then times t minus 8 pi x. This is the exact form. If I make a small approximation, I'll have y xt equals approximately 0.12 sine 175.773 t minus 25.133x, and that is going to be our progressive wave equation. Okay. All right. So let's move on now to question 9b. All right. So let us read question 9b. Okay. A 1.53 meters closed pipe makes a humming sound at frequency 282 hertz when the wind blows across the open end. The speed of the sound is 343 meters per second. With the help of a diagram, determine the number of nodes in the standing wave. Okay, so first things first, a closed pipe will look like this. It will look like, well, it's going to be a pipe, and then I'll have a node here and then an antinode here. So that means it's going to have waveform of some sort, of this sort. Okay, that also means that my wavelength is actually 4 times as long. My fundamental wavelength is going to be 4 times as long as my pipe. All right, now because v equals to f lambda, and because v equals to f lambda, that means I can determine the fundamental frequency simply by dividing the speed of the sound, or the speed of the sound, with the fundamental wavelength. Okay, so I can do that right now, okay, simply by substituting lambda with 4L. Just checking that I have all the values. I have V here, okay, I have V, and then I have L here, right? It's given earlier on the question. So I can know my fundamental frequency to be 343 over 4 times 1.53. Okay, so that is my fundamental frequency. I can, of course, calculate it. So 4 times 1.53, and that leaves me with approximately 56.05 hertz. Okay, so let us draw, because this is the fundamental frequency, let us draw the first overtone. So the first overtone, it's going to look something like this. It's going to make a full circle and come back, full and come back. All right. So for this one, it's going to be 3/4, right? It's going to be 3/4 rather than 1/4. Okay, so that means to go from here to here, we multiply by 3. So the first overtone is going to be 56.05 times 3. Okay, so 56.05 times 3. Okay, so that's going to be 168.15 hertz. Okay, now, so this is the first overtone. So first overtone, and then I can go on and do the second overtone. So again, like that. Okay, and that. Okay, so this is the second overtone. This, so going from fundamental frequency to the second overtone, will simply multiply 56.05 with 5, because it's going to be 5/4. So 5, 1, 2, 3, 4, 5/4. Okay, so 56.05 times 5 is going to be approximately, it's going to be 280.2 hertz. Because the the sound frequency that we heard when the wind blows is 282, we can say that what we're hearing is actually the second overtone. Okay, so it's going to be approximately 282 hertz. How many nodes is in the standing wave? Well, we can calculate 1, 2, 3. There are 3 nodes. 3 nodes in standing wave. Let me just underline that. Okay. All right. So that's going to be 3 notes in the standing wave. All right. Again, this second overtone is also known as the third harmonic. All right. Okay, so moving on to the last part of question 9. All right, so this question is going to be on Doppler effect. Let me just write that down. Doppler effect. All right, so this effect is actually what explains that how the frequency that you perceive can be higher or lower depending on whether the source is moving towards you or away from you. Okay. So let us just read the question. The frequency of a whistle by a moving train and the frequency heard by a stationary observer meaning that the velocity of observer is equals to 0, are 520 hertz and 460 hertz respectively. So that means the frequency, the original frequency, is going to be 520, and what is heard, right? What is heard is actually 460 hertz. Okay. All right. So the velocity of sound is 343 meters per second. Calculate the speed of the train. Okay, so that means the speed of the source. All right, so how do we work out? Right, we can use the Doppler effect equation, right, where it tells us the frequency heard by the observer. Let me just erase that. Heard by the observer over the frequency of the source is equals to V plus minus V observer over V minus plus V source. So again, the V simply means the speed of sound. All right, V naught, VO is the V observer, and Vs is the velocity of the source being the train. Okay, now we have the observer to be stationary, so that simplifies our work. Okay, and we have, right, the train moving away from us, right? We have it away from us because f prime is going to be 460 over 520, and this is definitely less than 1. Okay, so we want the bottom part to be bigger than the top, so that means my 460 over 520 must be equal to V over V plus Vs. Okay, so my V is going to be 343, my and then I'm looking for Vs. Okay, this is fairly direct to do. I can just key that into my calculator, and what I'll find is my Vs is approximately 44.739 meters per second, moving away from the observer. Okay, and that is all, right? That covers both the simple harmonic motion question as well as the sound wave or waves questions from PSPM 1920. All right, so if you like this kind of discussions, hit a like, share with your friends, and subscribe to this channel. Thank you very much. I'll see you in the next video. Thank you.